Well, hello, ladies and gentlemen. So we're going to continue on powering through the material, begin chapter 4 today, which is in the notes, which is the energy balance or conservation of energy. We'll have seen some of this material before. We looked at the first day of class. We looked at the conservation of mechanical energy equation, and I showed you that it was deficient in the sense that it lacked a few terms: heat, interaction, and the change in internal energy. So we've already looked a little bit at the energy balance, but let's start anew today by declaring the closed system energy balance, E-balance, sometimes called the first law of thermodynamics. Energy balance, or the first law of thermodynamics. Let me write down the most basic form of the energy balance. We have the heat minus the work is equal to the change in total energy. And energy is equal to kinetic, potential, and internal. So what that means is the change in internal energy plus the change in potential energy plus the change in kinetic energy. Okay? Now, if we apply this to some system, so here's our system, and it goes from one state to another. So this would be state 2, and this would be state 1. So this is our system. It has a certain amount of mass. It's a closed system energy balance. You don't see any mass being pumped in or being pumped out over the process. So this system with a certain amount of mass is subject to some kind of heat addition, Q1 to 2, and perhaps does some work, W1 to 2, over the process. So this energy balance for this system over the process will look like Q1 to 2 minus W1 to 2 is equal to the change in total energy from state 1 to state 2, which is the change in internal plus the change in potential plus the change in kinetic energy over the process. So that's the closed system energy balance applied to a system that moves between two states, state 1 and state 2. Now let me show you all the various forms of the energy balance. There are many different ways to write the energy balance, just like there are many different ways to write bases of heat transfer and work. Remember we had that table the other day? We had heat per unit mass. We had an infinitesimal process, so we had del Q. We had a rate base, which is del Q over dt. There are many ways to write the energy balance. So basis or bases of E-balance. There are a lot of different ways to write the energy balance, and depending on the problem you're working on, one may be more applicable to the problem than the others. So we have bases here. We have expression. And then, of course, we have units. Let's do SI. And, of course, English units. Okay? So let's first write the overall process version of the energy balance. So overall process. For an overall process, closed system, I'm just going to rewrite this equation right here. We have Q minus W is equal to delta E, which is equal to delta U plus delta PE plus delta KE. Okay, so that's the overall process energy balance. The units of all the terms are energy. So in SI units, it would be joules, and in English units, it would be BTU, British thermal units, all right? Now, I can divide this whole equation for the overall process. I can divide it by mass. And everything becomes lowercase or specific quantities. So I can do over all per unit mass. So I just divide every term by mass. And so I get Q minus lowercase w delta lowercase e is equal to delta lowercase u delta lowercase pe delta lowercase ke. All right, so that's per unit mass. That's another way to write the energy balance. It might be useful depending on the problem and what you're trying to find. There's also the infinitesimal or differential process. So differential process. If I take the derivative of this equation, so I get or total derivative, if you like, I get a little bit of heat transfer, del Q, minus a little bit of work, del W. Remember, work and heat are path functions. So you don't write dQ and dW here, you write del or delta Q, delta W. And then I have dE. Energy is a point function, so it's dE, not delta E. dE, which is equal to du plus dPe plus dKe. Okay, that's the differential or infinitesimal process. Oh, I forgot putting the units here. Overall process per unit mass. That's going to be energy per unit mass. So we have joule per kilogram, let's say, and we have BTU per slug or pound mass or something, okay? You could say. Differential process, just units of energy. So a joule and a BTU, all right? And then another version you might find interesting and useful, perhaps you'll encounter it, is the rate-based. Rate-based. So how do I get the rate-based? Well, I'm going to take the derivative of the overall process with respect to time. I'll take the derivative with respect to time of every term. And I end up with a Q dot minus W dot is equal to, so the time rate of change of heat, the rate in which heat is added to the system minus the rate in which work is done by the system is equal to the rate of change of total energy of the system. And that's, of course, equal to the rate of change of internal energy plus the rate of change of potential plus the rate of change in kinetic energy. So each one of these terms, for example, so this Q dot is actually del Q over dt. And this E dot, for example, is dE over dt. If you want to know what these terms actually refer to, dot means time derivative. Like in physics, dot means time derivative. So this is the rate based. If you have a problem involving time, probably a good idea to use the rate based equation. The units for this equation are energy per unit time. You have energy per unit time. So a joule per second or a watt. Watt, which is a joule per second, that's in SI units. And then You could do a BTU per second, but the traditional, for the English system, traditional unit is the horsepower. Could be horsepower, okay? Could be horsepower, all right? So there are 4 different versions of the energy balance, and depending on what kind of a problem you want to solve, either of these may be applicable. Most of the time, you're going to use overall process, most of the time. Some of the times, especially for purposes of deriving equations, and we're going to be doing that soon, you might want to use the differential process. Remember, we talked about specific heat. We define specific heat as the little bit of heat added per unit mass per small temperature change. So specific heat can be defined in terms of a derivative. So sometimes the differential process is the equation to use. And sometimes when you have a problem involving time, it's quicker just to go to the rate-based energy balance. Now, one last thing before we move on and do an example, I want to state that all these versions are equivalent. They all represent the same thing. They're just on a different basis. For example, if I start with the overall per unit mass, I can get to the overall by multiplying the equation by the mass of the system. If I multiply the overall process per unit mass by the mass of the system, all these become uppercase, and I get the overall process equation. How do I get the rate-based? Well, I can take the differential process and divide each term by dt. Change in time, differential change in time, and I get the rate-based equation. Okay? So all of these are versions of the same thing. They're all equivalent. I suggest that you memorize, and most of the time use the overall process. But once you memorize one version, you can always get the others. By taking derivatives, by dividing by mass, multiplying by mass. How do we get, for example, from the differential process to the overall process? Say we started with the differential process energy balance. How do we get to the overall process? You integrate over the process. And the del's go away, the d's go away, and you get Q minus W is equal to delta E, et cetera, et cetera. All right? So all these are equivalent. You either take derivatives with respect to something, you multiply by mass, you divide by mass, you integrate. These are all equivalent versions of the energy balance. Okay, let's take a break for a second, and we'll do a couple of examples involving the energy balance for a closed system. Closed system. Okay, so let's do an example here. Let's say we have a system. So here's our schematic. We have a system. It's a closed system. It starts off at state 1. The system then experiences some sort of work and heat interaction. Work is done on it or done by it, and maybe some heat is transferred. So we have Q added to the system from state 1 to state 2, and maybe work done by the system from state 1 to state 2. All right? And the system initially starts off at some energy E1 and ends up at an energy E2. So let me give you some numbers here. Closed system, the heat added to the system is 25 kilojoules over the process. So this is 25. Notice that it's positive. Positive, so heat is added to system. When Q is positive, that means we're adding heat. Then we have work done on the system. Work done on the system by an amount 500 joules. All right? So the system is receiving energy in the form of work. We're doing work on the system by an amount 500 joules as the system goes from state 1 to state 2. Notice it's on the system. The initial energy of the system, E1, is 10 kilojoules. What are we supposed to find? We're supposed to find the final total energy of the system, E2. So find the energy of the system at state 2. Okay, so let's begin here. Analysis. So we want to find an energy, and we have a bunch of works, and we have an initial energy. We want to find the final energy. So clearly the energy balance is involved here. We have energies and energy transfers, and we're trying to relate them. So now the question is, what version of the energy balance are we interested in? Well, let's go look at our versions here. So the problem indicates what kind of a process. We're going from state 1 to state 2. This would appear to be an overall process problem. The overall process energy balance is Q minus W is equal to delta E. Okay? So the change in total energy is equal to the heat added to the system minus the work done by the system. I want to emphasize here that W is defined as positive when it's done by the system. When energy is flowing out of the system in the form of work, W is positive. That's why there's a negative sign here. When the system does work, the energy falls for the system. That's why we have the negative sign. So I want to emphasize this work is done by the system when it's positive. Okay? So let's write the energy balance down for the overall process. So it's a closed system. We're told it's a closed system. There's no mass flowing across our system boundary. So here's our system. There's our system. There's no indication any mass flowing across the system boundary. So we're told it's a closed system. Apparently that's the case. So this is a closed system. Overall process. Okay, let's write the E balance for the overall process closed system. Q minus W is equal to delta E. And this is all from state 1 to state 2. What's delta E from state 1 to state 2? That's going to be equal to, this is the change in total energy. So it's equal to the final energy E2 minus the initial energy E1. Note, E2 is what we're trying to find. So this is good news. I already see an E2 popping up in the equation. That's what we want to solve for. Now let's figure out what these various terms are here. I have Q1 to 2. So I've got this, put a little check mark on top. I've got that. I have the initial energy, E1. I've got that too. What about the work? Now let's be a little careful here. The work, I have a numerical value for it. It's 500 joules, not kilojoules, but joules. And it's indicating that it is on the system. Now, work is supposed to be by the system in the energy balance there. So this is by the system, and this is on the system. So when I plug in the numerical value for work, I need to put a negative sign in front of this because the energy balance says this is work by the system. On the system, we're doing work on the system by the amount of 500 joules, but the energy balance wants that to be written in terms of by the system, so I have to put a negative sign when I plug in the numerical value here, okay? Suffice to say, I have the work. I just need to put a negative sign in front of the numerical value when I plug in to make it by the system. Okay, so I got those three quantities here. Let me solve for E2, which is what I want. E2 is equal to E1. Put this over on the other side of the equation. plus Q 1 to 2 minus W 1 to 2, okay? So I just move the E1 over on the other side of the equation, and then I flip the equation, and I get E2 is equal to E1 plus Q minus W. And I have all three of the terms on the right-hand side of the equation. Let's plug in. Let's plug in. Let me get myself a little bit more room here. Kind of running out of room. So let me move over here. So again, E2 is equal to E1 plus Q 1 to 2 minus W 1 to 2. Okay, let's plug in. E1 is 10 kilojoules. 10 kilojoules. The heat added is 25 kilojoules. 25 kilojoules. And then I have minus, and I need to put a minus 500 joules there. Minus 500 joules. Now, why is the minus sign here? Because this needs to be work done by the system. By system. Okay? That's why we have the negative sign, so we take work on the system and convert it into work by the system. All right? Now, one little thing here, the units need to be the same for all the terms. This is in kilojoules, kilojoules, joules. Ooh, we need to convert this. Let's see, for every 1 kilojoule, there are 1,000 joules. So the joules cancel out, and I'll get kilojoules in that term. So let's see here, what do I have? 10 kilojoules plus 25 kilojoules plus, the negatives cancel out and I get a plus 0.5, 500 divided by 1,000, so 0.5 kilojoules. Looks to me like 35.5 kilojoules. So E2, the final energy of the system, is equal to 35.5 kilojoules. So let's box that up, okay? 10, 25.5, 35.5 kilojoules. That's the final energy of the system. Final energy of the system. All right? That's pretty simple. So the key here is to remember that the work term in the energy balance is positive by the system. But we were given that work was 500 joules on the system. So I had to put a negative sign in front of the numerical value. It canceled out, and that's where the positive sign came from in front of the work term, okay? So you got to make sure you understand work in the energy balance is work by the system, okay? It's positive when it's by the system. Let's do another example here. Take a pause for a moment so I can get it set up. All right, ladies and gentlemen, let's do a second problem involving the energy balance here. Let's say that we have a room here full of people and some lighting equipment. So we have some electric light bulbs in a room, lighting a room. Maybe this is a conference room. Maybe it's a gymnasium. Who knows? So we have a lot of electric light bulbs here at the top. These are 100-watt light bulbs. And we have a number of people in this room. Maybe it's a gymnasium. Maybe it's a conference room. Maybe it's a classroom. Who knows? So we have N people or N persons, and we have N light bulbs in this room. Now, each person is radiating body heat at a rate of about 2,000 kcal per day. Typically, people consume around 2,000 kcals per day for their nutritional needs. So I'm assuming all of it, probably a bad assumption, but I'm assuming all of it is eventually being radiated out in the form of heat, body heat. So 2,065 kcal per day is the rate of heat rejection from each person in the room due to body heat. So we can think of each person radiating Q dot person into the room. So body heat is being rejected into the room, if you like, from the people that are in the room, all right? The electric light bulbs, and there are 10 electric light bulbs, 40 people, 10 electric light bulbs. Each bulb is 100 watts. So we can think of the light bulbs consuming or receiving, if you like, electric power. So each one of these bulbs is receiving electric power. W dot, what am I calling it? Bulb electric. So each bulb is receiving 100 watts of electric power, okay? Now, this is a cool room. It's a cool room and it's in a hot environment. So out here, it's hot. So hot environment or surroundings. Hot environment or surroundings. Well, what's going to happen, of course, is heat is going to get transferred from the hot surroundings into the cool room. That's what insulation is for, to reduce the heat transfer between a hot surrounding and a cool room, or a hot room, a warm room, and a cool surrounding. So we're going to get some heat flow from surroundings into the room. So we can think of heat being added at a certain rate from the hot surrounding to the cool room through the walls, and we're going to call that Q surroundings. And that's going to be 15 megajoules per hour. So that's the amount of heat being transferred into the cool room from the hot environment. Now, what's going to keep this room cool is an air conditioning unit. So out here, we have an AC unit. And the AC unit's responsibility or purpose is to extract out heat from the cold room and to keep it cool. There are all sorts of things that are conspiring to heat this room up. The heat transfer from the environment, the heat transfer due to metabolism from the people, so the body heat being rejected, and then the energy transfer, the work transfer from electric work or power to running the light bulb. So there are all these things that are adding energy to the room, and we need to suck that energy out or remove it using an air conditioning unit. So Q dot AC is being rejected or extracted due to the use of an air conditioning unit. Okay, so what are we supposed to find here? We know a lot of things, but what we don't know is how much of the heat load the air conditioning unit is responsible for. How much heat does the AC unit have to extract from the room? So let's find out how much heat the AC unit has to extract out, the rate of heat extraction due to the AC unit. Okay, so analysis. Let's move over here. So let's find out the amount of heat required or rate of heat extraction due to the AC unit to keep the room cool. So analysis. Okay, so this is an energy problem, obviously. We have a lot of heat flows going on. We have a flow of work, or transfers of work, transfers of heat. And then we want to find a heat transfer rate due to the presence of the air conditioning unit. So this is clearly an energy balance problem. What's our system going to be? What are we going to apply our energy balance to? Well, I'm going to surround the room with a control volume. And so this is going to be my system. System control volume, if you like, CV, system control volume, CV, all right? So my system is going to be the cool room, and I'm going to apply the energy balance to the cool room. All right, let me write down the appropriate version. Notice I have a lot of heat transfer rates. Everything in the problem involves a rate. So what version of the energy balance should I use? I think I should use the rate-based. So E balance Q dot. Oops, I think I'm going to need a bit more room here. Q dot minus W dot equals E dot. And E dot is the time rate of change of energy within the system. Within the system, all right? Now let's look at what some of these Q dots and W dots are. The heat transfer has a number of different sources. There's the Q dot to the system from the surroundings. So we got the Q dot from the surroundings into the cool room, so we'll have Q dot surroundings. We have the heat transfer out of the room to the AC unit. So that's out of the room. See the arrow indicates outflow due to the AC unit. And then we have a bunch of heat transfers to the room. And what we mean by that is the body heat being rejected by the occupants, okay? There are N people in the room, and each person is rejecting heat at a certain rate, Q dot person. So there are 3 different sources of heat transfer. There's the Q dot surroundings. We have the N persons times Q dot person. So that's the total heat transfer due to all N people into the room. And then I have minus Q dot AC. Notice the minus sign because this is outflow positive. I want to find Q dot AC, and I want that to be a positive number. And it's understood from the diagram, that out is positive. Out is positive. Out is positive, so that's why there's a negative sign in front of this Q dot AC, all right? What about the work term, W dot? What kind of work is going on in this problem? Well, remember there are 3 different forms of work. There's boundary work, electric work, and shaft work. There's actually a 4th kind of work, but we'll talk about that later. As far as we're concerned, there are 3 kinds of work. There's no shaft work going on. There's no propellers in here. There's nothing stirring the air around that I can see, so I'm going to assume that there's no shaft work. By the way, it's getting a little tight here. I'm going to write my assumptions here. Should be over here, but I'm out of room. So assumptions, no shaft work. I'll write that down in a minute. Is the boundary, is the system changing volume? This is my room here, and I'm making the room the system. I don't think the room is changing volume over this process, so there's no boundary work going on. So the only work left is electric work. So W dot equals W dot electric. Now the electric work or power being consumed by the bulbs is N bulbs times W dot bulb electric. And by the way, the assumption here is this is energy consumed. Bulbs are consuming electricity, not producing electric power. So this is consumption. Consumption, okay? In other words, we are doing electric work on the system. Electric power is flowing into the system to run the lights. So that W dot electric is on the system, not by the system. Consumption, or if you like, on system. So we're going to have a negative sign floating around here when we apply our energy balance, okay? So let's see here. W dot will be then N bulbs. And then I have W dot electric. And that's for, I think it says bulbs electric. Bulb electric. Now remember, this bulb electric is on the system. It's work, electric work being done on the system. The bulbs are consuming power. So electricity is flowing across the system boundary. Electricity is flowing across the system boundary to power the electric bulb. So W dot electric is on the system, not by the system. So I got to put a negative sign right here. On system. On system. Notice that W dot, the negative sign is going to cancel out with the negative sign in the energy balance, all right? Okay, so that's taking care of two terms. We'll make the substitution here in a moment, write out the resulting equation. What about this change in energy within the system over time? The change in energy within the system over time. I don't get a sense in the problem that the temperature is going up or down over time. This would appear to be a steady state problem. No changes with respect to time. The amount of energy within the room, the total energy, and that's related to temperature, is assumed to be constant. So I'm going to write up here steady state. Steady state. And what that means is dE dt. The time rate of change of energy within the room is 0. The energy doesn't change in the room. So what flows in has to flow out in terms of energy. Okay, what's transferred in the form of heat and work must be transferred out in the form of heat, let's say, Q dot AC, all right? So steady state, dE dt is equal to 0. All right, well, let's apply that to our equation, our energy balance. So this guy is 0. Why? Because we are in steady state, SS. Steady state, SS. Okay, let's write down what we got. Q dot surroundings plus N persons Q dot person, and then I have a minus Q dot AC, and then I have a minus, and now I got the work to the power terms from the electric light bulbs. Minus N bulbs, W dot bulb, and this is electric, and all of that is equal to 0. Okay? Now let me solve for Q dot AC. Oh, by the way, that cancels out and I get a plus sign right there. So let me move Q dot AC over on the other side of the equation and flip the whole equation. Q dot AC equals Q dot surroundings plus n persons Q dot person plus n bulbs W dot bulb electric. Okay? So now I have an expression for the amount of heat that must be transferred out of the room due to the AC unit. It's the heat transferred in due to the environment, the heat transferred or rejected due to body heat for all the people, plus the heat, plus the energy dissipated or consumed by the electric bulbs. All the energy that flows into the room has got to be transferred out due to the AC unit. Okay, the AC unit's dumping all that energy that's flowing into the room back out into the environment. Okay, let's see if we can plug in here. I think we're going to need a bit of space. So this is equal Q dot surroundings. Let's see here. Q dot surroundings. Q dot surroundings was 15 megajoules. So let me put that in per hour. 15 megajoules per hour. 15 megajoules per hour. I think I want to express Q dot AC in kilowatts. So I need to convert this out of megajoule and convert it into kilojoules. So there is 1,000 kilojoule per megajoule. So now I'll get kilojoules per hour, and I got to convert hours into seconds. So there are, for 1 hour, there is 3,600 seconds. So the hours cancel, and I get kilojoule per second when I go through and I do the calculation, okay? When I go through and I do the calculation. Okay, now let's attack the heat transfer due to the metabolism of the people. So we got N people, 40 people. We got 40 people, and they're rejecting heat at a rate at 2065 kcal per day. So I got 40, and then I got 2065 kcal per day. Okay. Kcal, let's see here. There are 4 point, as I recall, there's about 4 kcal. Let's see if I can get it here. Hold on a second. There's 4.2 kcal per kilojoule. Kcal per kilojoule. 4.2. So 1 kilojoule is 4.2 kcal. So the kcals will cancel out, and I'll get kilojoules per day. I want to get kilojoules per second, which will be kilowatts. So I need to convert out of the day into seconds. Let's see here. There are 1 day is 24 hours. And there is 1 hour per 3,600 seconds. Notice the hours cancel out, the days cancel out, and I end up with kilojoules per second in this term once I do the conversion, okay? And then I got another term involving the electric power for the light bulbs. I have 10 bulbs, and each bulb is consuming 100 watts, and there are 1 kilowatts per 1,000 watts. Notice the watts cancel out and I get kilowatts for the second term. That's exactly the unit I want. Okay, let's see what we get here. Let's just crank this out and see what we get. Hopefully we'll get something good, something decent. Let's see here, 15, so let me tack each term here. So you got 15 times 1,000 divided by 360. So I get 4.16 kilowatts. That's kilojoule per second, so that would be a kilowatt. That's the Q dot surrounding term. That's the Q dot surrounding term. And then I have the heat rejection from the people. Let's see here. 40 times 2065 divide by 4.2 divide by 24 and then divide by 360. 0.227 kilowatts from the 40 people. That seems about right. Kilojoule per second, that's kilowatt. And then I got the energy consumption from the electric bulbs. So that's going to be 10 times 1,000 or 1 kilowatt. 1 kilowatt. So let's add this all up. 4.16 plus 0.227 plus 1, and I get 5.3. Actually 5.3, 5.4 kilowatts. So Q dot AC, the heat transfer or the heat load on the air conditioner, Q dot AC is equal to 5.4 kilowatts. That's how much heat the air conditioner has to extract out from the room to keep the room cool. All right? That's a nice little problem because it involves a bunch of unit conversions. You see here the importance of units. Those of you that are not keeping your units in your calculations, you're just begging for trouble. Begging for trouble big time. If you lose a unit and the units aren't compatible in your terms, you can't figure out why you're getting the wrong answer, you can waste hours trying to chase down what you did wrong. Keep your units with your numerical values and then do your conversions in the equation, okay? 5.4 kilowatts. 5.4 kilowatts. Okay, let's do another problem involving use of the tables, in particular properties for ideal gases. Let's do one involving use of some tables. Let's say we have air in a rigid container. Now this rigid container, so what does rigid mean? It means the volume is constant, it can't be distorted. This air in this rigid container initially has a temperature T1, a pressure P1, and a volume V1. And then heat is transferred in such a way to cool down the air to bring it to T2. So in a rigid container, we start off with some temperature T1, and it gets cooled, or the temperature is brought down to T2. Let me give you some numbers here. Initially, the air is at a temperature of 500 degrees Kelvin. The pressure is 0.25 megapascals. That's 2.5 bar. So it's approximately 2.5 atmospheres. And the volume is 3 cubic meters. The final temperature is 300 degrees Kelvin. So we're cooling the air down by transferring heat. Okay? So what are we supposed to find in this problem? We're supposed to find the pressure once the air has been cooled down to temperature T2. And we're also supposed to find the heat transfer required to cool down the air, so Q1 to 2. Find the heat transfer, find the pressure at the final state, okay? We'll deal with assumptions as we go along here. We'll deal with assumptions as we go along. Okay, let's get started. Let's get started here. Analysis. Analysis. Well, so we want to find the heat transfer. The energy balance is a place where heat transfer comes in. So why don't we write the energy balance for our air system? By the way, before I get started, let's make sure we define our system here. You need to know what you are applying the energy balance to. So our air is our system. Air system. So the air inside the container is our system, all right? So let's apply the energy balance. Q, 1 to 2, minus W, 1 to 2 is equal to the change in total energy from state 1 to state 2. And that's equal to delta U from 1 to 2 plus delta KE from 1 to 2 plus delta PE from 1 to 2. Change in internal energy, potential, and kinetic energy from state 1 to state 2. Okay, let's whittle some of these terms down and see if we can get rid of some stuff. Okay? Notice that we're supposed to find the heat transfer to or from, maybe Q 1 to 2 will be negative, so we're supposed to find the heat transfer to or from the air. So this is what we're supposed to find, so let's attack this term. The work, what sort of work is involved with this situation? Well, remember there are 3 forms of work as far as you're concerned at the moment. There's boundary work, shaft work, and electric work. You see any wires in this problem? Any resistors in this container? I don't see any, so there's no electric work. Are there any shafts in here? Is there a propeller in here that's spinning around and applying a torque with some angular velocity and therefore transferring work in the form of shaft work into the system? Nope, I don't see any shafts, any propellers or impellers, so there's no shaft power or shaft work. What about boundary work? That has to do with the change in volume of the system, the work that the system does as it expands or gets compressed. One's positive, one's negative. It says it's a rigid container. Rigid container. I take that to mean constant volume and therefore no boundary work. So rigid container. So this implies to me that it's an isochoric process. Make sure isochoric process, constant volume, and that implies W bound equals 0. Rigid container, isochoric process, no boundary work, no shaft work, no electric work. So I'm just going to write here W 1 to 2 equals 0. No work. No work. Okay, so let's go to our energy balance here and we'll cancel that term out. No work. That's gone. Okay, let's attack some of the other terms here. The change in internal energy has to do with the change in either phase or temperature of the system. The temperature of the system is definitely changing, so I don't think I can get rid of the delta U term. But I can, I think, neglect the change in kinetic and potential energy of my air system. I don't get any sense in the problem that the air is moving, that it's accelerating, that it's slowing down, and I certainly don't get a sense that the position of the tank or the rigid container is moving. So there's no change in gravitational potential energy of the system. So I'm just going to assume these away. I'm going to assume these away. So I'm going to write here in my assumptions. This is where the assumption section starts coming important. I'm going to write delta KE 1 to 2 is equal to delta PE 1 to 2, and I'm going to set those both equal to 0. Starting to run out of room there already. Okay? So this implies Q1 to 2 is equal to delta U 1 to 2. All right? Now, I'm going to be using tables here to evaluate the change in internal energy. Let's have a quick look at these tables. Here's one out of the text. If you go right after specific heats, which we discussed in the previous lecture, you will see table B11, ideal gas properties of air. Enthalpy, internal energy, these are specific enthalpy and internal energy are a function of temperature. So we're interested in specific internal energy values here, and they're going to be changing for our system as it cools down. So I need to rewrite the delta U term on the right-hand side of the energy balance in terms of change in specific enthalpy, a specific internal energy of the system. So I need to write this as the mass of the air in my system times delta lowercase u from 1 to 2. And so that's going to be equal to the mass of the air in my system minus U2 times U2 minus U1. Okay? Now, I don't know the mass of my system and I don't know the internal energy. I'll tell you what, before we get too far into this, let's calculate the pressure at state 2. Let's just do that. I forgot we were supposed to do that. I kind of got ahead of myself. So let's calculate the pressure at state 2. So how are we going to calculate the pressure at state 2 before I do the heat transfer? Well, why don't we assume ideal gas behavior? We can check it if we want. So I'm going to write here, oh boy, I'm out of space, but I'm going to start loading more stuff up here. How about we assume IGB valid? Ideal gas law valid. If IGB is valid, then I can use the ideal gas law. So let me write the ideal gas law. So IGB valid. So pressure times volume is equal to mass times a gas constant times T. Okay? Now, how can I get pressure 2 without doing a whole bunch of work? Without doing a whole bunch of work here. How can I get pressure 2 without doing a whole bunch of work? How about I evaluate the ideal gas law at state 1 and I divide it by the ideal gas law at state 2. PV1 equals MRT1. And now I'm going to divide it by the ideal gas law at state 2. P2V2 MRT2. Now, a couple of things. The M and the R can be canceled out. They're constants, the gas constant for air and the mass of the air. Also, the volumes are the same. V2 is equal to V1. Why? Because it's an isochoric process. V2 is equal to V1. Why? Because it's an isochoric process, rigid container. So V2 is equal to V1, and we can cancel out the volumes. Okay, so what does this imply? I'll take the P2 over here, and I'll flip the T1 and the T2 and put it over on the other side of the equation, and then flip the equation. So I have P2 is equal to P1. And then I have T2 over T1 right there, okay? Now, what is P1? P1 is 0.25 bar, and T1 is 500 degrees, and T2 is 300 degrees. So I know everything. equals 0.25, megapascals. T2 is 300 degrees Kelvin, and T1 is 500 degrees Kelvin. Remember, you got to put temperatures in Kelvin. Temperatures are given in Kelvin, but whenever you're using the ideal gas law, remember temperature is absolute, so it's got to be in Kelvin or Rankine, okay? Kelvins cancel out, and I get megapascals. So let me crank this out. 0.25 times 300 divided by 500. 0.25 times 300 divided by 500. And I get 0.15 megapascals. So, P2 equals 0.15 megapascals. Let's box that up. Okay, that's a fairly easy calculation. Notice I did a bunch of algebra. I tried to be a little bit smart with my algebra so that I didn't have to go through and at least not yet calculate M and R and all that sort of stuff. Okay, I just did some cancellations. All right. Okay, so we got the pressure, P2. Let's get back to calculating the heat transfer. Let's calculate the heat transfer. I don't know a lot of things here. I don't know the mass of my system, and I don't know the internal energies at state 1 and state 2, specific internal energy. Let's see if we can calculate some of these things. Let's go to table. Let's go back to the table and look at the specific internal energies of the air at 500 and 300 degrees Kelvin. Let's see here, specific internal energy, air, 300 degrees Kelvin is 214.07 kilojoules per kilogram. 214.07, so let me write that down over here on the board. U2 is U evaluated at temperature of 300 degrees Kelvin, and that's 214.07 kilojoules per kilogram. And that is from B, what's the table? B11, okay? And 500 degrees, 359.49, 359.49, 359.49. So U1, 359.49 kilojoules per kilogram. And that's U evaluated at 500 degrees. Let me get this off here so you can see what I'm writing. Okay. So I've written the specific internal energies from table B11 at 300 degrees and 500 degrees. So now we can plug it into our energy balance. I have these two now. I have U2 and I have U1. The only thing is I don't have the mass of my system. Oh, where are we going to get the mass? Well, let's use the ideal gas law. Let's use the ideal gas law. Let's see here. PV equals mRT. So the mass is equal to pressure times volume divided by the gas constant times temperature. Okay? Now I got the pressure, I got the volume, the pressure at, so let's evaluate this at state 1. Let's evaluate this at state 1. So that's equal to P1 V1 over RT1. I have the pressure, I have the volume, and I have the temperature at state 1. They are 0.25 megapascals, 3 cubic meters, and 500 degrees Kelvin. We're gonna have to be careful of units here. Have to be a little careful with units. So let's see here. 0.25 megapascals. And the volume is 3 cubic meters. Oh, the gas constant for air. Well, the gas constant for air is going to be the universal gas constant. R universal divided by the molecular weight for the air. So let's look at that. The gas constant is 8.314 kilojoules per kilomole degree in Kelvin. And the molecular weight for air, let's look that up again. There we go. Air, 28.97 kilograms per kilomole. So this is going to be 8.3 kilojoule per kilomole degree in Kelvin divided by 28.97. 28.97. Make sure I have enough chalk here. Kilograms per kilomole. Okay, the kilomoles cancel out and I get kilojoule per kilogram degree in Kelvin, which is the unit for my gas constant. Temperature, T1 is 500 degrees Kelvin, okay? Notice the kelvins cancel out in the gas constant, okay? Now for the units to work out right here, this megapascal has to be expressed in terms of kilopascal, so it cancels out with the kilojoule in the gas constant. So let me convert out of the mega. So there's 1,000 kPa per 1 megapascal, and the megapascals will cancel out, okay? Let's see what the mass is. Let's put that all in the calculator and we'll see what we get. We'll see what the mass is. Let's see here. So 0.25 times 3 times 1,000 divided by 8.3 divided by 500. I'm going to multiply that by 28.97. And I get 5.23 kilograms. 5.23 kilograms. Okay? A pascal is a joule per meter squared. No, joule per meter cubed. Sorry about that. Or a Newton meter per meter cube, or a Newton per meter squared. So the pascals and the kilojoules and the cubic meters, these guys all cancel out, okay? So 5.23 kilograms. So now I got the mass. 5.23 kilograms, and U2 is equal to 214. 214.07 minus 359.49. And these both have units of kilojoules per kilogram. Notice the kilograms cancel out, and I get kilojoules here. So I'll get Q1 to 2 in terms of kilojoules. Let's see here. 214.07 minus 359.49, and that's going to be multiplied by 5.23, and so I get 760 kilojoules. Negative, sorry, there's a negative sign here because U2 is less than U1. Negative 760 kilojoules. Negative 760 kilojoules. Okay? So let me write that up here. negative 760 kilojoules. Q 1 to 2 equals negative 760 kilojoules. What does the negative sign mean? It means heat is being transferred out. Oh, sorry. There you go. Molecular weight, universal gas constant, did the unit cancellation, 5.23 kilograms. I got the mass now, 5.23 kilograms. I plugged in my internal energies that we just looked up, and I get negative 760 kilojoules. Why the negative sign? Heat transfer is out of air, or if you like, from / out of air. Heat is being extracted from the air, okay? We defined heat transfer as being in positive, so we got a negative sign, and what that means is heat is being transferred out of the system, okay? By the way, we can check this problem doing sort of a back of the envelope check to make sure our numbers are right. We can use specific heats. Why don't we do that? Why don't we do a little back of the envelope problem? Let me get rid of this. Let's do a little check. Let's do this problem in another way to get an approximate answer. Here's our mass. I'm going to leave that. So let's not apply the energy balance, but let's use specific heats. So recall, CV is equal to delta Q over M dt. So that's the definition of specific heat at constant volume. We have a constant volume process going on here. It's in a rigid container. So I can solve this for del Q. Del Q is equal to CV M dt. And I can integrate that. And I can integrate it. So Q1 to 2 is equal to the integral of del Q from state 1 to state 2, which is equal to the integral of specific heat at constant volume times the mass of my system times dt. And that's from T1 to T2. Now I'm going to do a little hand waving here. And I'm going to assume constant specific heats. Let's see if we can assume constant specific heat over the process to at least get a ballpark answer. So let's go look at specific heats for air. Specific heats for air. Superheated vapor table, specific heat, air. So we go from 300 to 500 degrees Kelvin. If I evaluate CV at 400 degrees, which is the average temperature, notice it's not really changing a lot between 300 and 500. It looks like maybe about 5%. I'm going to assume CV evaluated at 400 degrees, and I'm going to use it to calculate my heat transfer, to estimate my heat transfer. 0.726 kilojoule per kilogram degree in Kelvin is my specific heat. So I'm going to evaluate this guy. I'm going to let this be the average specific heat, and then I can pull the mass and the specific heat out of the integral. Approximately equal to CV at T average, which is 400 degrees Kelvin, times the mass of my system times the integral of dt, which is delta T. Delta T 1 to 2. Okay? So I got Q1 to 2 is approximately equal to the mass times CV evaluated at 400 degrees Kelvin, which is my average temperature. And then I have delta T, which is T2 minus T1. I have the mass, CV again. Let's see here, what was CV? 0.716 as I recall. CV at 400 degrees Kelvin, 0.716 kilojoule per kilogram degree in Kelvin, and that's from table. Make sure I got the right number here. Oh, I'm sorry. I'm sorry about that. Let's share it one more time. Got the wrong number here. So CV for air at 400 degrees is 0.726, and that's from table B10. 0.726, sorry about that. 0.726. And that is from B, oh, I'm losing it here, trying to finish up. And that is from B10, from B10. Okay, let's plug in. The mass was 5.23 kilograms. Specific heat evaluated at 400 degrees was 0.726 kilojoule per kilogram degree in Kelvin. Notice the kilograms cancel out. And then I've got delta T, which is 300 minus 500, and that has units to Kelvin. The kelvins cancel out in the specific heat, leaving kilojoules. Let's see here, what do we get? Hopefully we'll get something very close to the correct value, which is the value using the property tables. Let's see here, 5.23 times 0.726 times 200, and that'll be negative 759.4 kilojoules. So the true value using the exact properties out of the property tables is 760 kilojoules. I probably did a little rounding there. Assuming constant specific heat evaluated at the average temperature, I get 759 kilojoules. So Q1 to 2, negative 759 kilojoules, and this is from specific heat. Okay, assuming a constant specific heat. This is a back of the envelope check for our correct calculated value. Good idea when you do a calculation to be able to do it get it from different means, okay? So let's get this cleaned up. The actual heat transfer is 760 kilojoules out of the system. And from constant specific heats, we verified that using the definition of specific heat, constant volume, it's an isochoric process, and we get 759 kilojoules, very close to 760, okay? Good check, good check. So I'm gonna put a check right here, check, that looks good. If you wanna go through and check that IGB is valid, I think you'll find that it is. The reduced temperature, the minimum temperature in the system is 300 degrees Kelvin. The critical temperature of air is what, 133 degrees Kelvin. So you're going to get a reduced temperature min greater than 2. And I think you'll find the pressure is what? What's the critical pressure for air? Is it 33 or 37 bar or something like that? 37 bar. Air, 37 bar. Our pressures Our maximum pressure is going to be P1, the pressure falls, is 2.5 bar, so we're definitely below 0.2. So IGB, you can check it, it is valid. Take care, ladies and gentlemen. That is all. I think I've gone a little over time. So take care.